Um, let's begin the lecture today. In chapter 5, we discuss the electro, we discuss the magnetostatistics in vacuum. Here we consider the magnetic fields with matters, just like what we did in chapter 2 and 3. Um, sorry, 2, 3, and 2, 4 in electro statics case. And just a reminder that the homework for chapter 5 will be due this Thursday, and so it's on November the 4th. Now, similar to the response of material to electric field. So if you put a material into the inside a magnetic field, then electron spins will be respond to the magnetic field, and the electron spin itself can also be think of the electron spinning around its own axis. So it sort of produces a current along this center of the mass of the electron itself. And this current is actually correspond to the leading order term in the multiple expansion. So in electrostatic case, the leading order term is the electric monopole, but in magnetic case, the leading order term in multiple expansion is the magnetic dipole. So here, each electron spin will possess a finite magnetic dipole M. And so here this I is the current carried by this electron, and the A is the area spanned by this current loop. So you should think of an electron semi-classically as a ball, and this ball will rotate around its own axis. Even though this picture is actually incorrect, so if you think of the electron as a finite size ball, and then in order to produce a magnetic dipole such large, the rotation of this electron must be exceeding the speed of light, which is impossible. So the classical explanation of this magnetic dipole fails, and we have to use quantum mechanics to explain this. And in quantum mechanics, we actually treat the electron spin as the intrinsic property of the electron, just like what we treat of the mass. So now we know already that an electron spinning around the own axis will produce a magnetic dipole. And however, if we pair two electrons together, so if we pair a spin up electron and a spin down electron, then the total angular momentum of this pair is zero, and correspondingly, the total magnetic dipole moment is proportional to this total spin of the electron. So the total magnetic dipole moment will also be zero. And now you can see that depending on the material, some material has completely filled electron orbitals, such as helium and argons, and some of the materials has unfilled orbitals like hydrogen, lithium. So you imagine that depending on the materials, the material might respond to magnetic field differently because of this filling or incomplete filling of these electrons in these orbitals. Now, applying the magnetic field to the electrons will introduce this magnetic dipole, and how this magnetic dipole responds to this magnetic field is something that we want to study in this chapter. So I just talk about the materials that have incomplete field shells. So in this kind of materials, there are at least one unpaired electron, and this unpaired electron has the magnetic dipole. So just like how electric dipole respond to the E field, this magnetic dipole will also tend to align with the magnetic field. And for this kind of material, we call them as paramagnetic. So the magnetization is parallel to the B field. And for a material with completely filled shells, then there are no unpaired electrons. So the total magnetic dipole moment is 0, and it will actually respond differently to magnetic field. As we will see later today, hopefully, that the magnetization developed by this material actually can be opposite to the magnetic field. So this is something that we haven't seen in electric field. So this is something different. And also, similar to the electrostatic case, there are also permanently polarized materials. And for this permanently magnetized materials, we actually call this as ferromagnetic. So for ferromagnetic, if you apply a magnetic field to it, the ferromagnetic will remember the history of the magnetization. So if you if you magnetize an ion, and it will actually become a magnet, and this is the most classical magnetic field that we see in everyday life. So in this chapter, the content is actually highly parallel to the content we've learned in the polarization by an electric field. So here the intrinsic property is the magnetic dipole. So we want to study how a magnetic dipole interact with the magnetic field. So just like the electric dipole case, for electric dipole, we if it's polarized, we can always divide this polarized material to infinitesimally small dipoles and consider them a collection of this integration of all this infinitesimally small dipole. Here, for the magnetic dipole case, we can do similar things. So say that we have a current like this. We can always divide a large current into smaller currents. You can imagine that the currents inside will completely cancel each other, and what's remaining is the outermost current. So here, no matter how strange your outermost loop a magnetic dipole could be, we can always divide that into small segments of rectangular loops. So for easy to understand, we study the interaction between a magnetic dipole to an external magnetic field by this simplified model. So, but remember that even though it's a simplified model, our conclusion still applies to generically shaped magnetic dipole. So say that we want to consider how this rectangular loop interact with this homogeneous magnetic field, say pointing along the z-axis upwards. And now if we look at the force felt by this magnetic loop of current, so the force should be I cross proportional to I cross B, if I remember correctly. So here, if you look at the force along all these 4 segments, the force along the segment here should be if you try to determine the direction of the force, that will be I cross B going up. So the force will be pointing outwards and to the direction over there. And likewise, if you so you have to use the right hand rule to determine the direction of the force. Is that correct? Okay. So similarly, you can determine the force along the loop, along the line segment over there. That should be the exact opposite, because here we simply rotate our direction of the current. So on these 2 segments, you can see that the magnetic field actually stretches the 2 segments, but the total force is still balanced. And now we can also determine the force along the loops on this segment and that segment. So if you apply the same if you apply the same right hand rule, I think you should always get a force that's to the outside. So if you combine all the forces, it seems that the total force is 0. However, similar to the electrostatic case, even though the total force is 0, there is still a net torque into this magnetic dipole. So here the figure on the right hand side is look from this angle over here. So you can see that one is a force pulling to the left, another is a force pulling to the right. So this torque will try to align the magnetic dipole to the magnetic field itself, just like the case in the electrostatic case. So remember that even though polarization has 2 different forms, in both forms, the electric field will try to align the dipole to its direction. So here the result is exactly the same. So if we calculate the total torque, that should be an R cross F, and you can, if you do the integration, I think you can see that the torque should be AF sine theta along the x direction. Okay.
Is just how do we define R in calculating the torque? Is it just about some random point, or
Oh, so here I'm calculating the with respect to the center, the origin.
Is it important that it should be centered?
Yes, yes.
Okay.
Because that's the natural choice. So here you can, I believe if you calculate the, mm, here the sine theta is the angle between the uh, uh, here sine theta is between the plane and the axis, and you can imagine that the torque will become the largest if you set the m and the z to be perpendicular to each other, because in that situation, the force should be um, so in this case, the force will be the torque will be in extreme position like this, and if you set theta, so this is theta equals pi over 2, and if you set theta equals 0, then that's the case where this m direction is parallel to the b direction. So in this case, the total torque will be 0. So that I believe that should explain this torque formula. And for the force, it's simply the um, I cross B formula, and but except that you need to integrate um, along this line, and so here the B is the length of this direction. So here this length is B. So then if you combine these two formulas, you can get the total torque, and it can be actually, so here I times AB is the total current times the area of this rectangle, and now you can combine this to the total magnetic dipole moment M, and this sine theta is actually can be expressed as a cross product. So now if we express the expression in a coordinate free form, the final answer will be the torque is actually equal to the magnetic dipole moment across this magnetic field. So I wonder if you still remember the conclusions for dipole moment in electric field. The answer is that the torque produced by a dipole uh, in the homogeneous electric field that is also P cross E. So they are extremely similar here. Now we can generalize the conclusion to a general field. So instead of a homogeneous field, we can try to calculate what's the force magnetic dipole might feel in an inhomogeneous magnetic field. So for example, I'm giving a very simple case here. So consider a solenoid here by wrapping currents along a cylinder. Then the magnetic field is produced is something like this. So there is a radial component of this magnetic field. So the magnetic field itself is inhomogeneous. So in this case, if you try to calculate the force felt by this current or this magnetic dipole moment, you can see that because the magnetic field is along the there is a radial component of this magnetic field B, and if you cross that with this current direction, which is pointing into the screen, and so the force produced by each line segment will be pointing downwards. And if you go around this loop, the force will always pointing downwards. So there is a total force that's pushing this loop of current towards this solenoid. And if you get the exact calculations, so the force should be I cross B integrating along this loop. And so the length of this loop is 2 pi r, and the current is I, and then the cross product with the B field give you the B cosine theta. So the theta is the angle here. So do you have a question?
Yes, because I don't know, I don't understand. The current now for the right figure is for the rightmost point where we label F and B. We have current as upward vertically. Huh?
感觉打气有眼睛开什么
Oh, I
Go
I don't know where the I direction is.
So the I is going the loop here. So it's at this point, it's pointing into the screen.
Oh, okay.
这个眼睛
It's hard to imagine. Okay.
So at this point, the current direction should be into the screen,
Okay.
and at this point, it should be out of the screen.
Oh my, okay, oh. Okay, then, okay.
Okay. So so now if we generalize the result to a general case instead of this special case, the actually the final formula is a very simple one, like del operator, the divergence of this m dot b. So here this formula means that we can immediately rewrite the we can immediately get the potential of the m interacting with the B field, because the potential because the force is related to the potential by del u. So we simply identify the inside being the negative of a potential. So the potential energy of spin interacting with the magnetic field B is simply m dot b with a minus sign. And I believe that I've also have you calculated the potential for electric dipole in electric field. So the formula is actually similar. That is minus p dot e. It should be the homework problem of homework 3. So now you actually see that the electrostatics is quite similar to the magnetostatics. So if you want to know how to prove the equation here, so you can see the problem 6.4 or 6.24 in the Griffith on how to prove it. So the general idea is that here, if you can tailor expand the magnetic field in the vicinity of the point of infinitesimally small magnetic dipole. So even though the leading order term, that is which is a constant term, doesn't contribute anything to the force, the next leading order term, so that is a gradient of magnetic force, that will produce a force. So in fact, this gradient of magnetic field is what has been used in a Stern-Glach experiment. So I don't know if you have already heard of this experiment in quantum mechanics or not, but the Stern-Glach experiment is really one of the foundational experiments for quantum mechanics, and this is actually, even though it's a first step of this Stern-Glach experiment. So for atoms or for electrons with spins, the Stern-Glach experiment can actually separate the spins with different angular momentum or different internal spins into two different directions because of this force. So this magnetic field gradient give you a force that depends on your dipole moment, magnetic dipole moment m. So for spin up, the particle or the atoms will fly, say, upwards, and for spin down, it might fly downwards. So this experiment actually can split the it can split a flow of atoms into two different branches, and so in quantum mechanics there are also follow-up selections of this. So in the actual quantum mechanics experiment, there will be additional magnetic fields to further separate the spin down, say, to another two. But depending on the direction of the magnetic field, it actually helps you understand the superposition principle in quantum mechanics. So if you are interested in that, you can simply look up the Stern-Glach experiments in Wikipedia. I think that will give you some hint. So now, if we compare what we get in the electrostatic and the electrical magnetostatic case, so here all these equations. So for the potential energy, the force, and the torque, they are almost equivalent to each other. So if you still remember the equations that I gave during lecture 9 for the force, it's actually written slightly different. So in the homework, I believe you use this equation to evaluate the force of a dipole interacting with a E field, right? So this equation can actually be rewritten into the equation over here if you believe that the curl of an electric field is 0. So if you have, I can upload exercise on how to prove this, but I believe that you can also find this as one of the problems in Griffiths. Now, because of this analogy, we can actually think of a magnetic dipole being a copy of an electrical dipole. So even though in reality the magnetic dipole is an infinitesimally small current, the current loop over here, and the electrical dipole has the charge plus and the negative charge minus sign here, we can sort of draw an analogy by saying that instead of believing that the magnetic monodipole is produced by this current, we can made up of this current by a magnetic monopole, north pole here, in the similar to the plus charge, and a south pole replacing the negative charge. So this model can give you some of these magnetostatics correctly, but not all of them, because apparently there are no magnetic monopole. So you might get something incorrect if you use this simple magnetic dipole model. Okay, so here we just discussed the how a magnetic dipole will respond to the magnetic field. And as we just said that for paramagnetic materials, the material has an unfilled electron shells. So for this unfilled electron shell orbitals, the magnetic dipole will try to align with this external magnetic field. And so this case is similar to the polarized materials in electric field. And this explains the paramagnetic materials. And now, next we will discuss the diamagnetic materials, which cannot be explained by this simple electron spin. So for this diamagnetic material, we have field electron spin orbitals. So a spin up is always paired with a spin down. So the total M produced by atom is always 0. So a magnetic field cannot align the intrinsic spin magnetic moment to the magnetic field itself. So in this case, now we have to consider that the electrons not only rotate along the axis of its own, it also revolves around the nuclei in the center. So imagine that this is the orbit of the electron. So inside here there is a nucleus, and so this orbit is actually huge comparing to the orbit of an electron rotating along its own axis. So now here the electron rotating along this nucleus will also produce a magnetic moment M, because you can sort of think that because the electrons rotate along this orbital, there are always charge going across this across the screen by whenever you reach a period of t. And so even though technically speaking this is not a magnetostatic case, because there is a charged particle moving. However, because this moving speed is not approaching the speed of light, and we are also interested in the field that's near this orbital. So in this case, the magnetostatic can still approximately be valid. So now you might argue that, say that here this orbit produce a magnetic moment, then it will be similar to the paramagnetic case, that this magnetic moment will also try to align with this magnetic field. So technically speaking, this is the correct. So in the sense that we initially have atomic orbitals going in random directions. Now, if you try to apply the magnetic field, the orbitals will actually prefer to be aligned with this direction of the magnetic field. But in high temperature or in normal temperature, in room temperature, this effect is actually small because the orbital here is actually huge comparing to the magnetic dipole moment of spin rotating around its own axis. So even though there are tiny bit of alignment with the B field, this effect is almost negligible. And we actually don't consider this as an effect that can be useful at all. So instead of, so even though there are paramagnetic contributions in this problem, because the contribution is small, we can simply neglect the effect for now. So now, what else can this happens for orbital inside the magnetic field? So to know what this electron orbital will do under magnetic field, we start from a zero magnetic field and then pump up the magnetic field to see what happens. So in the case of zero magnetic field, then we can calculate the current. So just like what I mentioned earlier, you can calculate the current by counting the total charge passing a point over here, say. So the per unit time, right? So the total charge passing this point is negative E, and the time it required to pass that point is simply the period, so the T. So if you replace the T by the omega over 2 pi, then you can further replace this omega by V over R, and then you get the equation here. So here the minus sign is simply because the charge of electron is negative. And now the total dipole moment by this electron orbit is simply the I times the directional area. So the area is pi r squared. So if you calculate the m, that will be pointing downwards along the z direction. So that's because if you use the right-hand rule, the current is going in the direction like this. So remember that the velocity is inverse direction of the current because of the for the electron. Now, if we add a magnetic field to this problem, so we've already discussed this point, and now without this magnetic field, the electrons will orbit around the orbital here, and you can imagine that's the centripetal force. So the centripetal force is simply the force responsible for the rotation, right? So the centripetal force is simply entirely provided by this electric force here. So that force will be E squared over 4 pi r squared. So that is the because of the Coulomb law times the Q and times the Lorentz law. Now this force will be equal to the m v squared over r. If you still remember this classical mechanics equation. So I've copied the equations over here. However, if you apply if you apply a magnetic field, the electrons might speed up or slow down, because you can imagine that the magnetic field also applies a force to this moving charge. So there will be an additional centripetal force provided by this magnetic field. And if you still remember the Lorentz force law, that is QV cross B, right? So if you here in this case, the V, if we apply the B field along the D direction, then V on the right hand side is into the screen, and the B is upwards, so it's there will be a force that's pushing outwards. So this is the sorry. So the magnetic force is pushing outwards, so it will actually slow down the motion, right? So because the centripetal force is reduced, and reducing centripetal force will slow down the motion of the electron. Now we can count. Oh, I might be. Oh, sorry. The charge is negative, right? So I think I made a mistake. So the charge is negative. So I actually add an additional minus sign. So I didn't consider the negative charge of the electron. So the force should be instead pointing inwards. Okay, so this means that the electron will speed up instead of slowing down. And now let's say that the new velocity is v bar. So now we correctly identify that the v bar should be greater than v, right? And that's because the centripetal force is added to this electrical force, and it's a positive sign. So for the new v bar, we can actually calculate it, and assuming that this is a small magnetic field B, then we can assume that this delta V is small. So here here we replace this V bar minus V by the delta V, and Taylor expands the equation over here, and then we can linearize and determine what the delta V should be in terms of the magnetic field B. So do I need to explain a bit more? Okay. okay. So the idea is that you can, in principle, solve the equation here, and determine this B bar as a function of a magnetic field B, right? And because here you can see that this is a quadratic equation, and so you can solve for this V bar by in principle this equation can be solved. And however, if we think the delta V is small, then we can instead Taylor expand the equation, this expression, and the Taylor expansion, assuming the b as a small parameter, and so this Taylor expansion will eventually give us the expression here. So here, how this one did is to instead of doing the Taylor expansions, a trick here has been done. So now I believe the trick is to simply here comparing terms. So here it moves the this equation to the right, and let me see. So sorry, so it plug in the equation here to here, and then move to the right, right? So you will get the equation over here. So this is simply combining the equations here, and then the next step is to this is simply the mathematical identity, right? But the way why it want to be written like this is because you can identify the v bar of minus v as a small parameter. So here we replace this one by this delta v. It's small, but here the v bar is close to v, right? So we simply replace this by 2v, and now we also
2v bar.
yeah, 2v bar or 2v, like
But in order to cancel with the other side, you have to be 2v bar.
yes, sure, you can also replace this v bar by v, right? Then you simply cancels out the v bar on all the v here. Then you can see that delta v is simply proportional to the magnetic field B, right? But you can always brute forcefully solve the v bar as a function of B, and then do a Taylor expansion of your solution. That will give you the exact same thing.